Hi, it's time for us to dig a little bit deeper into our embedded systems. So in this set of lecture slides, we're going to leave JAG and TOIT behind, and I'll motivate why, and explore how we can use our microcontrollers using a lower level of programming than we have thus far. So in the sequence of these next few videos, we'll talk about the following subjects. I'll go over what the end goal is for our robot. It'll help quite a bit if you sort of know what the goal is at the end of all of this. And by the end, I mean, what do we want to be able to do by the end of the semester? I'll mention just briefly, and this is something we'll cover again and again, is the project workflow. So how do we actually set up our system? How do we program it? How do we test it? Then we'll talk about the hardware and software for our particular microcontroller and the systems that we're using. And we'll end with a bit of a discussion of something you may or may not have heard of before, the Arduino ecosystem. So let's start by talking about the task for our robot. The task for this semester is a little contrived, but essentially we want our robot to drive around a course. And I'm going to add some additional requirements there so that we can explore the different type of sensors and actuators that I've purchased for your kits. We also want our robots to avoid obstacles. So imagine your robot's driving around and there's a box in the way. It should know how to go around the box and then continue on. There are a set of really simple algorithms called the bug algorithms for doing simple obstacle avoidance like that. We also want our robot to avoid crashing into dynamic obstacles. That's a little different than what I just described with obstacle avoidance, and the main difference is just how fast it needs to react. If our robot's driving along, and all of a sudden we step our foot down right in front of it, we want it to react quickly. And so we'll implement something called emergency braking for that. Slightly different technique than avoiding obstacles, and in fact, for both of those we could use the distance sensors that we'll incorporate in a couple of weeks, but in particular it's going to be extremely important for this task. We could use a slower acting sensor for something like obstacle avoidance. Namely, we'll also have cameras later that can be used for obstacle avoidance. And speaking of the cameras, probably the most complicated task we're going to ask our robots to do is to follow signs. We could do this with traditional computer vision techniques, but we're going to use TensorFlow Lite. And machine learning algorithms. We actually won't delve much into machine learning in this class. Instead, we'll create a quick data set and use an online tool from Edge Impulse. To upload models to a secondary microcontroller that I'll introduce later in the semester called the Grove Vision AI board. Clearly this is a bit of a contrived task. I've tried to set up a task that means that we have to use these different sensors, and a few others that I haven't quite mentioned. Just the ability to drive around a course, and like an obstacle course, will require us to know where we are and what direction we're currently heading. So for that, in just a short while, I'll introduce both an IMU, an inertial measurement unit, and a magnetic compass. The compass will actually be the first thing that we introduce that you don't already have in your kits. So how do we go about solving or writing algorithms or designing a robot to navigate such a course? Well, throughout the semester we'll keep revisiting this idea of requirements. what do we need to change? What do we need to update this time around? And then using those requirements, we'll design our software. Then clearly you'll program your software. You'll upload your programs. And currently we're doing that with jag run. Later on we'll see that there are sort of many different ways. The first thing we'll do is just to use Arduino and click the upload button. That's part of the Arduino IDE. Later on in the semester we'll focus on doing that with Wi-Fi using OTA, over-the-air updates. And once our program's uploaded, we want some way to communicate back and forth, so we can monitor and direct over Wi-Fi or WebSockets. That's similar to how we've implemented the heartbeats so far. But we'll expand that interface so that we can send data in both directions, as well as just pinging to let each other know that the microcontroller still exists and that the user controlling the microcontroller still exists. This whole area is known as embedded systems development. Embedded systems is pretty similar to what you've already seen. The biggest difference between this and writing a program in Python or Rust or OCaml or Haskell or whatever you've seen in your classes is, compared to that process you've seen before, here we are really designing something for a specific piece of hardware. You may not even considered the hardware you were using when you were programming in Python, whether you were on a M1 Mac or an x86 64 Windows laptop. It didn't really matter. Here it's going to start mattering quite a bit more. We'll also have a lot more limited resources. That includes things like memory and speed and storage and just overall capabilities. Our network speeds are going to be slower. We're going to have fewer things running at any given time. You may have run into stack overflows while programming in Python, but trust me, that'll happen a lot more quickly if you try to write a recurrent function for your microcontrollers. Your development environment is quite a bit different. Specifically, you're not actually programming on the system on which your programs will run. You may not have ever actually thought about it, but when you program in Python, that Python script will be running on the laptop or desktop or whatever machine you're currently programming on, 9 times out of 10 anyway. Maybe there's some that are using Chromebooks for programming. In this case, we'll be programming on your laptops, desktops, or the lab machines, and then your program itself will be compiled and then uploaded to a separate machine on which it'll run. That means we have a lot more limited functionality on how we can monitor the output, whether we can use print statements or something like GDB. We can use those tools, but in a much more limited fashion. We also have a less standardized way of interacting. And by that I mean we're not using a mouse and keyboard to control the microcontroller. Instead, we can only send commands over Wi-Fi or upload new programs over serial. We typically don't have an operating system. So we can't ask the operating system for help, essentially. We're not asking the operating system to grab something from a file system or send something over the network. Instead, we'll be using a library directly for those things. So no OS levels of abstraction. Normally, on your computer, you can run many processes at the same time. So you might have Spotify open at the same time you have a web browser open, at the same time you have PowerPoint open for creating a presentation for senior seminar. For the most part, we'll have a single flow of execution that's running on your microcontroller. It's not going to be doing multiple things at the same time. That's not technically true, especially for the ESP32 that we're using, since it has a second core. It has a dual-core processor, and that second core is often used for sending things over Wi-Fi. For the most part, though, we are going to model our programs based on a single execution thread. All right, that's where this video will end. In the next one, we'll talk specifically about what hardware we do have at our disposal.